Next, we consider a case where there are many independent variables, and this is called multiple linear regression. So the basic assumption is that the expectation value of the dependent variable depends on all the values of x's. Okay, which means this is intercept and one parameter and one variable, another parameter, another variable, and so on. Let's say there are m independent variables with corresponding parameters. Okay, so for this problem, we have data like this: y1, x1, x1, 1, x2, 1, 2, 1, x3, 1, and xm1, and y2, x1, 2, x2, 2, x3, 2, and xm2, and so on. So that means we have a huge number of, well, it depends on number of data and independent variables. But anyway, so these are the linear equations we assume to hold. So alpha beta 1, x1 1, beta 2, x 2 1, beta 3, x3 1, and beta m xm1. So y2 alpha plus beta 1 x1 2, and so on, xm2. So we have n sets of data. So beta 1 x1 n and beta m xm n. Actually, there should be error terms and error n. Okay. So of course, we assume that these errors follow normal distributions and they are independent, of course. So the problem now is to determine all these parameters: alpha and beta 1 and beta 2, beta 3, and up to beta m. So there are now how many parameters? 1 plus m plus 1 parameters. So how can we do this? But the idea is the same. So first we calculate the ordinary s squared, which is the sum of squared errors. So that would be from 1 to n, and yi minus alpha minus beta 1 x1 I minus, and so on, beta m xm I squared. And the idea is the same, and we are going to minimize this quantity. So how can we do this? Again, idea is the same. So we differentiate it. So s squared, we differentiate s squared with respect to alpha. then what do we get? So, just it's just ordinary differentiation. So we have I to yi alpha minus beta 1 xi and so on. Well, just skip it, and minus 1 equal to 0. And also we differentiate it with respect to beta 1, and we have this. And minus x1i equal to 0. And similar equations for beta 2, beta 3, up to beta m. Okay, then we solve this equation. How do we do this? Now, from the first equation, since this is equal to 0, we can just cancel this negative 1 and this 2. Sorry, this 2 should be gone. Then, let's see what we have. So, from the first equation, we should have, let's see, yi minus n alpha minus beta 1 ix1i minus beta 2 ix2i and so on, and beta m, well, let's and minus beta m xmi equal to 0. Okay, so divide everything by n, so we get rid of this, 1 over n, and 1 over n, 1 over n. So that will be y bar minus alpha minus beta 1 x1 bar. Okay, x1 bar is the average of x1 i's, right? x1 bar and so on, beta m x m bar. Just to make sure, x1 bar is the average of x1 i's. Okay, and similar for xm bars equal to 0. So we have this equation. From this, we can have an equation for alpha, which is y bar minus, let's write in the summation form. So let's say j, beta j x j bar. Okay. And from the second equation, this one, let's get rid of this negative sign and this 2. So we have let's see. So we have I yi minus alpha minus, let's say, summation of, let's say, j. So I from 1 to n, this is the number of data, and j from 1 to m, which is the number of coefficients for x's. So xji times x, wait a minute, x1i, right? x1i equal to 0. So this is x1i. So let's see. So if you distribute these things, we have I x1 I y I minus alpha x1 I summation over I, and let's see, this one is a little bit complicated. I j x j I times x what x1 I equal to 0. Okay, so let's see. Oh, wait a minute. Yes, should be okay. And let's see. So if you divide everything by n, you get this would be like x1 y bar, right? So this is the average of x1 something times y something, and minus alpha x1 bar, so that's this. And this one, what's this? Let's see. So I runs from 1 to n. So I think we should swap the summation here. So this should be sum over j and the average of xj x1. Oh, wait a minute. Beta is missing somewhere. There should be beta j. Yeah. So beta j and beta j on here. So this one, xj x1 bar, is the average. So let's write it more explicitly. So this is the sum average of I from no, not j I from 1 to n. So that's the average over data points. Okay. So xj I x1 I. Okay. So that's what we have. And if you put this alpha into here, then you should get something like, well, it's not actually easy, but you should get something like what? x1 y bar minus x1 bar times y bar. So does this look familiar? And also minus, let's see, sum of, wait a minute, sum over, let's see, sum over j from 1 to m and beta j and xj x1 bar minus xj bar times x1 bar equal to 0. So again, we have covariance here. Covariance between, let's say, y and x1 minus sum of beta j, and this is again covariance, right? Covariance between xj and x1 equal to 0. Okay. Now let's expand this. So if we do this for x2 and x3 and up to xm, we have a series of linear equations. It's simultaneous linear equations. So that would be like, let's see, covariance. Why don't we just abbreviate this? So let's say, let's see, okay, Cj is covariance between y and xj. Okay, and let's say maybe djk would be covariance between xj and xk. Okay, if you write this, we have the following simultaneous equations. So that would be C1 is equal to beta 1 d11 plus beta 2 d 21 and up to beta m dm1, and C2 is beta 1 d12 beta 2 d22 and so on, dm2 and so on. So this is a system of linear equations. So we can express this in terms of matrix and vector form. So C1, C2 up to Cm, we have let's see, actually this is a symmetric matrix. So djk is equal to dkj. But anyway, well, let's stick to okay, so let's see, we can express this as like d11 d12 and d1m and d21 and dm1 and dmm, and we have beta 1 beta 2 up to beta m. So this is unknown, and this vector is calculated from the data, and this matrix is calculated from the data. So if we can invert this matrix, then we can solve for betas. So let's, for the moment, assume that there is the inverse of this matrix. So in that case, we have beta 1, beta 2, and this matrix up to beta m is given by the inverse of this matrix times C1, C2 up to Cm. So this is how you get beta 1, beta 2 up to beta m. And once you determine the values of beta, you can substitute this beta into this formula to find the value of alpha. Now you can find it. Okay. And this beta is a vector, and you can form a vector of sample means of x's, right? x1 bar, x2 bar, xm bar. So this is actually a dot product between two vectors, beta 1, beta 2, and beta m. So dot product. So that means alpha is y bar minus beta vector and x bar as a vector, right? So formally it looks quite simple. Okay, so now we have assumed that there is the inverse of this matrix, but what if there isn't inverse? It's possible, and you should think about this. Okay. So far we've been discussing linear regression, which was to model a set of data by a straight line, or a straight line in multidimensional space. But in practice, we often find some data that do not fit linear line, right? So, for example, if we have some data like this, it's of course, if we apply the linear regression, it's always possible to have a line, right? Linear regression. It's always some result is obtained. But sometimes it's better to fit a curve instead of a line. So in some cases, it is possible to apply the technique of linear regression to do some nonlinear regression. So that is called curvilinear regression. For example, we can model the dependence of y on x in terms of a quadratic function. For example, beta 1 x and beta 2 x squared. So in that case, we may model some quadratic function. We can fit a quadratic function to the data. But how do we find these coefficients? Exactly. So how do we do it? Actually, it's quite simple. First, we replace, let's say, this x, rename it as x1 is x and x2 is x squared. So in that case, this equation is reduced to alpha plus beta 1 x1 plus beta 2 x2. So this is just a multilinear regression with two variables, right? And actually you can apply the same technique in many cases. For example, what if we want to, for example, in the case of RNA's plot, maybe we want, if you remember, that was like this. So log of chemical reaction was fit with some constant with this. Okay, so if you think this t as the independent variable, then this is a nonlinear uh, problem. However, if you, let's say, so y is log k and x is 1 over, let's say, negative 1 over t, then the problem reduces to y equal to a plus bx, right? So you can use ordinary linear regression. And yeah, you can use, depending on the problem, first look at the data and see what kind of function is appropriate. Maybe you can apply something like log of x, or even sine x, or whatever function, or maybe plus c sine square x, and so on. You can do this for any problems. But of course, there is some limitation because if the curve is more heavily nonlinear, something like So instead of some simple function like this or some periodic function or like this, maybe the data might look like very complex. So in that case, no simple function can fit this data. So in that case, we have to use some really nonlinear regression, which is beyond the scope of this lecture. But maybe you have heard of neural networks, artificial neural networks, or deep learning, or machine learning. So what they are doing is actually mostly just nonlinear regression like this. So fitting some data into some complex uh, functions. Not complex in the sense of complex numbers. It's a complex in the sense of complicated. Okay, so that's linear regression and non multilinear regression and curvilinear regression.